On this adventure in algebra, we're going to cover one of the first major theorems in this course. It's called Lagrange's theorem. So, given a group, I'm leaving off some of the hypotheses for right now to make this statement as short as possible. I'm going to say them out loud. Given a group G and a subgroup H, we're going to let G divided by H be this set. It's the set of all cosets of H and G. Then Lagrange's theorem says that the number of cosets is equal to the size of G divided by the size of H. The goal of this video is going to be proving this fact, and we're going to be doing it by relying on the fact that the cosets come from an equivalence relation. In fact, these are equivalence classes. So why does any of that matter? Well, here's a fact we might remember about equivalence relations. Given an equivalence relation on any set, if you let C1 through CR be the equivalence classes, then the size of X is the sum of the sizes of the equivalence classes. That's true in generality. Remember, we defined a specific equivalence relation with regards to a subgroup, such that the equivalence classes were the cosets. In particular, the size of this equivalence class is the size of the coset. What we just determined is that all the cosets have the same size as the subgroup. So the size of your group is the size of each of these cosets. These each have the same size. What happens when you add the same number up several times? Well, don't be stupid. Just multiply that number by the number of terms. So G is the size of H times the number of cosets. So congratulations, you've now discovered the number of cosets is equal to the size of G divided by the size of H. Congratulations, we've now proven a theorem. Let G be a finite group, let H be a subgroup. Then the number of cosets of H and G is the size of G divided by the size of H. In particular, the number of cosets is always a divisor of the size of G. As a result of this theorem, we often use this notation, G mod H, to represent the set of all cosets of H and G. I wish we didn't use that notation, but it's to remind ourselves of this theorem. The reason why I say I wish we didn't use that notation is that we still use this notation even when we're talking about abelian groups. So it's something you still have to get used to. Particularly since this division symbol does not actually mean division. And so that's one fact. The other notation we sometimes see is that we define this size, the number of cosets. We also call this the index of H and G. So it's the number of cosets. And it's also denoted by this. Don't ask me why it didn't occur to me to use G colon H for the set of cosets, but oh well. So, for example, the set of all cosets, we'll let G be the dihedral group on 4 vertices, and we'll let H be the rotation subgroup. Well, we already know by these calculations how many cosets there should be. How many elements are there in D4? Well, there were 4 reflections. Plus 4 rotations. And how many rotations were there? Well, there were 4. And so how many cosets are there going to be? Two cosets. So by doing this calculation, we know the size of the coset space should be 2. and one of the cosets should be H itself, the subgroup. So by doing this calculation, we saved ourselves a lot of effort. We only need to find one other coset. What can we do? Well, just take a reflection. Here, to be careful, we need to label our permutation. How about the reflection 1, 2, 3, 4? There we go. That's all we need. There's 2 cosets, and that's all of them by this theorem. All right, as another example, let's suppose we wanted to compute all the cosets of this cosets collection. The group is D4 again. The subgroup is this permutation. Again, for context, here's our square. 1 to 3, 2 to 4. This is the 180-degree rotation. So it's a group of order 2. So by Lagrange's theorem, the number of cosets is the size of the group divided by 2. 8 over 2 is 4. So it's going to involve more work than the previous one. We're not going to just take a random element in G, take away H, and call it a day. We're actually going to have to do some work. Well, at least we know what the first coset is. The first coset is H. That's known as E and R squared. So it's up to you if you want to use permutation notation or this other notation. I'm going to switch to this RS notation because I find it a little easier to calculate with. Well, we need another coset. So we need to start looking at elements that are in G but are not in H. Well, R that'll work. RH. There's 2 down. 2 to go. So what else do we need? None of these involve S's, so another obvious choice would be SH. We should have S and SR squared. And, well, here's 6 of my elements. By the way, the reason why I'm actually calculating these cosets down here is because now I've reached a point where I need to figure out a 4th choice. And so if I wrote R squared H, I'd be wrong because R squared H is equal to RH. If I wrote R squared H is equal to H. If I wrote R cubed H, I'd be wrong because R cubed H is equal to RH. If I wrote SR squared H, I'd be wrong because that's right here. And so on and so forth. So by listing these elements, I make progress. Because I know whatever I should pick next, it needs to be an element that's in G, take away all the previous cosets. Similar to how you compute cycle type or cycle notation for a permutation. Once you close off a cycle, you pick an element that hasn't appeared before. Once you've calculated a certain set of collection of the cosets, if you're not finished yet, you look for an element that doesn't appear in any of your cosets, and you choose that as an element in the next one. I guess RS. Or would that have been a good choice? SR to the negative 1 times R squared, that's just SR. That ends up being SR cubed. Yeah, that works. This calculation I just did showed that's the same thing as if you did SRH, by the way. Either one of those two answers gives you the same thing, actually. So congratulations, we found the 4 cosets in this coset space. One more horrible example. Boy, this one's going to drive me crazy. We'll do S4 modulo the cyclic group generated by 4 cycle. How big is S4? Why, it's 4 factorial. How big is this cyclic group? It has order 4, so I get 3 factorial, which is 6. There are 6 cosets. So yes, this is going to take a while. H has the identity, 1, 2, 3, 4. The square of that cycle, which is 1, 3, 2, 4. And then the cube of that cycle, which is its inverse. All right, so I need 6 cosets, which means I need an element that's not in one of these first 4 permutations. Well, I guess we can take the permutation 1, 2. And I hope you don't mind, I'm going to go ahead and just speed through the calculations. All right, so speeding through, if you multiply on the left by 1, 2 for all these permutations, these are the 4 you get. 1, 2 cycle, 2, 3 cycles, and this 4 cycle. I'm gonna have to keep track of what elements appear because, well, it's gonna take some effort. I notice 1, 3 does not appear, so I can try 1, 3 as well. So if I multiply by 1, 3 by each of these 4 permutations in H on the left, these are the permutations I'm going to get. I get 2, 4, so I see I'm not going to be able to, if I multiply by 2, 4 for this coset, I'm going to get this coset back, so I'm not going to do that. So far I have 4, 8, 12 permutations out of 24. I still have my work cut out for me. I haven't seen the permutation 1, 4 show up yet, so I'll try that one next. So after that calculation, I get these 4 permutations. It's worth pointing out these choices are arbitrary. The reason I'm picking 2 cycles specifically is because I find those to be the easiest for me to calculate with. But that's just an arbitrary choice I'm making. So I have 1, 2, 3, 4 cosets so far, and I need 6, so I need 2 more to go. That's all the 2 cycles involving 1 by itself. 2, 3 never appears as a 2 cycle, so I can try 2, 3 next. Two, 4 did in fact appear. So the only question is, are these 2 the same? If they're not, then these two would give me distinct two cosets, and if they're distinct cosets, then I'm done. Because then I'd have two more cosets, which with these four would give me 6. And why would that work? Because we also see that the 2-cycle 3-4 also never appears anywhere. So 3-4 is not an element in any of these 4 cosets. So 3-4 is distinct from each of these. So as long as I can show these two are separate, then I can finish the job without doing the calculations. This is an attempt to skip the last calculation. So when you get down to the last two, you can also do guess and check. Just guess 2 elements and prove that they give you distinct cosets. Technically, I could have done that all along, but I sometimes find it's easier to list to save myself some hassle. That's if and only if 3-4 inverse 2 3s in H. That's 3-4 inverse, 3-4 2 3. What is 3-4 2 3? Well, 1 goes to 1, 2 goes to 4, 4 goes to 3, 3 goes to 2. Yeah, that's not an H. So these are distinct. So 1 coset, 2 coset, 3 coset, 4 coset, 5 coset, 6 coset. So there's an answer. Is the answer unique? Well, no, because I could have replaced 1, 2 with this permutation, and that just replaces this coset with the same coset with a different representative out in front. Or I could have placed 1, 3 with 2, 4. There's another application of Lagrange's theorem. Suppose H is a subgroup of G, and G is a finite group. Then the size of H has to be a divisor of G. Why is that? Because we determined that the number of cosets was given by this formula. This number is a positive integer. So in particular, this has to be a natural number, which of course means that you better be able to write G as H times an integer. Ergo, H has to divide the order of G. And so this tells you that you can't find an element of order 2 in Z mod 5Z, because if you had an element of order 2, it would be a subgroup of order 2, and 2 does not divide 5.